So let's talk about the physical address and the cache today. So cache memory is a special, very high-speed memory. It is used to speed up and synchronizing with high-speed CPU. Cache memory is costlier than main memory or disk memory, but economical than CPU registers. Cache memory is an extremely fast memory type that can act as a buffer between CPU and a preliminary memory or secondary memory, between RAM and the CPU. So it holds frequently accessed data and instructions, so they are immediately available to the CPU when needed. So cache memory is used to reduce the average time to access data from the main memory. The cache is a smaller and faster memory which stores copies of data from frequently used main memory location. So there are various different independent cache in a CPU which store instructions and data. So for example, the current CPU design, they have level 1 cache, level 2 cache, level 3 cache. Usually level 1 cache is smaller, the smallest, and level 2 cache slightly bigger than level 2, and slightly bigger than level 3, slightly bigger than level 2. So because accessing memory, accessing the data, the average time that costs to access data is one of the main bottleneck in CPU performance. One instruction for calculating something, even if pretty complex, usually just take a couple clock cycles, but accessing data could take hundreds cycles to access from the main memory. So that's why we need to study the cache design or memory architecture design. I think one example that I could give how important the cache is or the speed of the memory is, I remember I had an old laptop and I replaced that old laptop with SSD from the mechanical hard drive to the SSD. Although I'm not replacing the cache that is embedded in the CPU, but you can see, but I can feel this performance speed up like immediately. It's almost like I bought a new laptop. So the memory access will actually affect the computer performance a lot. And before we talk deeper about cache, when the processor needs to read or write a location in the main memory, it first checks for a corresponding entry in the cache. So if the processor finds that the memory location is in the cache, then we got a cache hit. So basically, if we can find the data in a cache, then we got a cache hit. And otherwise, if it doesn't, then we got a cache miss. If there's a cache miss, then there's a penalty involved. So we have to dump the data from the original cache block, loading up the new data from the memory, which takes cycles, takes sometimes hundreds of cycles. So, now it's easy to understand. Like the performance of cache memory is frequently measured in terms of a quantity called hit ratio. So number of cache hits divided by number of cache hits plus number of cache misses is called hit ratio. We can improve the cache performance using higher cache block size, higher associativity, reduce miss rate, reduce miss penalty, and reduce the time to hit in the cache. So basically, we are trying to improve this figure, reduce this figure, and also reducing the cache hit time and reducing the cache miss penalty, so we can get an overall better design. But there's a problem. Remember the physical address representing like where the data actually is, right? But our cache size is pretty small. It's impossible to put all the data from the physical address to the cache. So we need to design a mapping logic. And this is why we talk about associativity, talk about tag index and offset. So you can see on the right hand side we have a physical address consists of like number of bits, and this one being consists of three main components. First one is tag, second one is index, and the third one is offset. So the index bit is being used to identify which set we are like writing and writing, and offset bit being used to identify which block of memory inside one block or line. So let me interpret it in this way. So we have a cache here. This cache being divided into several smaller spaces. So like for example, this is we have set 00 and set 01. Although like the set index shouldn't like in this case we have more than two spaces. It shouldn't just use 2 bits, but it's just one illustration. So we need to use like some bits to identify which set we are talking about. So imagine like we have a big city, and that city being separated into several areas or several places. For example, the Greater Vancouver area, we have like Vancouver, we have Richmond, we have like other places. So basically, identifier for each of the set, for each of the block of space in a cache, and inside this one set, we can separate into 2 smaller spaces, which we call line. When we have, in this case, we have 2 small, like we have 2 lines that will result in associativity equal to 2. Basically, associativity represents the number of lines inside one set. And when we find the data, usually when we find like 1 byte of data, we need to go to that line. And usually one line, or we call it one block, has like 10 bytes, 20 bytes. So which bytes are we referring to? Then we need to use offset bits to find, okay, this is a set, this is a byte, this is the data that I want to access. So the offset bit being used to identify which block of memory inside one block or line, and index bits being used to identify which set that I am referring to. Then in this way, we can find out the data from the cache. And then the rest of the bits are the tag bits. So from here, you can say if we have 4 sets, then we need to use in total 2 bits to identify which sets that I am referring to, because 2 power of 2 equal to 4, right? 0, 0, 0, 1, 1, 0, and 1, 1. Similar to the offset, the line size or the block size will determine the number of bits for the offset. So let me repeat. Offset bit size will determine the size of block and the line, and index bits will determine the number of sets. Okay, let's check out this question. So in this question, we have a table and gives a parameter for number of different caches. And recall that M is a number of bits of physical address, and C is a cache size, so B is a block size, and E is associativity, and S is the number of cache sites, number of cache sets, and T is the number of tag bits, S is the number of set index bits, and B is the number of block offset bits. So let's check out the first one. Remember I previously said, for example, this is a cache, and inside the cache that we divided into several space, which we called set. This is a set 1. Let me check. The question 1 said the E equal to 4. That means associativity equal to 4. That means we have 4 blocks or lines in one set. That means we have 4 identical sized lines or blocks inside one set. And we do know the block size. The block size is B, is equal to 4. So each of them is 4 byte size. So 4 byte, 4 byte, 4 byte. Because we know the block size, so first of all, from B, we know the block size is equal to 4B. And what we can know? We can actually know the small b is 2 bits. Because we have 4 bits, we have 4 bytes for each of the block. In order to identify each of the byte, we need to use 2 bits. For example, 00, 01, 10, and 11 to represent each of them. So we know the b equal to 2. And the question here, next question, what is S? S is the number of catch sets. So since we know inside one set we have 4 blocks or 4 lines, and now what is the size of one set? That is equal to 4 times 4, right? 4 is the first 4 is number of the first one is associativity. The first one is associativity, and the second one is a B. So we know inside one set we have 4 lines, and the size of each one is 4 bytes. So in total for one set is 16 bytes. And we do know that the cache size equal to 1024. Then we use cache size divided by the size of each cache, that is 16 byte. Then we got in total the number of sets. That is equal to 64. So the S, the capitalized S, is equal to 64. Since we know we have 64 sets, then how many bits we need to use to like identify each of them? That is, then we need 6 bits, because 2 power of 6 equal to 64. So S is 6 bit, S equal to 6. And we do know that one physical address consists of tag, index, and offset. So what is the size of bits of tag? That is equal to 32 minus the bits of index, that is 6, and minus offset bits of offset minus 2. That's equal to 24. And this is 24. So this is how we do the first example. The rest questions are very similar. Just by applying this logic, you can find out the answer of the rest. Okay, let's check out this question. So this question, this problem tests your ability to predict the cache behavior of the following C code. And okay, so we have a 2-dimensional array X. This X, we have 2 columns, and in each row we have 128 objects. So that's in total 2 times 128. And oh, by the way, the size of integer is equal to 4 bytes. So in total, the size of this is equal to, okay, so the total size of the 2-dimensional array X is 1024 bytes. Assume that we execute under the following conditions. First of all, size of integer is equal to 4 bytes. And second, array X begin at the memory address 0x0 and stored in row major order. So what this means? This just means the X00 being stored in address 0x0, and X01 being stored in 0x4, because each size of the integer is 4 bytes, and 0x2 we got 0x8, and all the way to 0x0 that is 0x512. Then how about x10? Just plus 4. That is 0x516. By the way, the binary representation of the 516. Let's convert 516 to binary. That's 1 0 0 0 0 0 0 1 0 0, and then from here all the way to x1 128. That is 0x1024. Okay, so in each case below, the cache is initially empty, and the only memory access to the entries of array X. All other variables are stored in register, and the code is stored in the L1 I cache, so the instruction cache, different from data cache in the data may be loaded. So that basically just means the instruction being stored in a different cache and data being stored in L1 data cache. So we only need to consider the data access to the two-dimensional array X, and assume that okay, let's just do one question. Assume the cache size is 512 bytes, directly mapped. So that means that the cache size is 512 byte, and associativity equal to 1. So direct map just basically means E equal to 1, associativity equal to 1. And we also know the block size. The block size is equal to 16 byte. In terms of a graphic illustration, is we have a cache here. For example, this is one set. Then inside this one set, we only have one line, and this line is 16 byte. By the way, 16 bytes, that in 16 bytes block, we can store 4 integers. So in another way, we can say we can store 4 integers. Each of them is an integer. Let's do the first question. Okay, estimate the miss rate. This is an interesting question. Okay, let's do this. Since the cache size is 512 bytes, and the block size is 16, so we can know the number of sets is equal to 512 bytes divided by 16 bytes. That's equal to 32. So in terms of let's refer back to this tag index offset. In this case, is 2 power of 5. Then we can know the index is 5-bit. This is 5-bit. And for how about the offset bit? Because we know it's 16 by the block size, so 2 power of 4. Then we can know the offset is 4-bit. So this is 4-bit. By the way, we previously checked the binary of 0x516. You will know why I need to check that. And from this C code, we can see the sum. Basically, what we're doing here is just sum up all the integers inside this two-dimensional array. But the accessing sequence is x0i plus x1i. So when I equal to 0, that is we are accessing 0, 0 and x10. So there are some interesting things in cache. For the x00, we do know the address is 0x0, so it's all 0. Let's just give some arbitrary number of for it, and for this one, for the 10, the representation is 10 0 0 0 0 0 1 0 0. Okay, sorry, it's not being aligned perfectly. Let's just, we can add some zeros in front. We have a lot of other bits in front of it. So the offset bits is the last 4 bits. These are the offset bits. And here we have 5 bits is index bits. So this 5 bits is index bits. Oh, you can find an interesting thing. It's actually the index. By the way, the index will determine which set this memory block is mapping to. In this case, they all mapping to x00 and x10. They all mapping to set 0, set number 0. So in terms of a graphic illustration, there's only, by the way, there's only one line inside the set 0, the set number 0. So when x00 is accessing the data cache, we got a cache miss, and then we load up new data. So when we load up the 00, because the size of this line is 16 byte, that means we can store 4 integers. So we are loading up 00, 01, something all the way to 03, and then the 10 and then x10 try to access the data. We go to the same set. We found, oh, it's different, but cache miss again. So if we access data in this order, in x0i plus x1i, if we access data in this order, we always get cache miss. So for the 00 to the 03, we always get cache miss on the set 0, and then on the set 1 we will get cache miss from 04 and 14 all the way to 4, 5, 6, 7, and 1, 7. So we constantly get cache miss for this case as well. So in this question, in question 1, the cache miss rate is equal to 100%. So it's 100% cache miss rate. Then how we improve this? There's one way to improve it, just to increase associativity inside one set. Instead of just using one line, we can replace it to 2 lines. If we have 2 lines, then we can successfully reduce the cache miss rate from 100% to 25%. How? It's just simply because when we are accessing, for example, we're accessing 00, then we cache miss at the beginning, then we load up the other data, and we got a cache miss from here, then we load up another new data. Sorry, we reduce it to the 50%, because if we still keep the size of each set remain unchanged. For example, that's for each of them we only give them 8 bytes of space. That means when we fail to load up 00, we will load up 00 and 01. Then for the next time, when I equal to 1, we got a cache hit. But for the I equal to 2, we got a cache miss. I equal to 3, we got a cache hit. In this case, we can reduce it to the 50%. So that's why in the second slides, I mentioned one of the way of decreasing the cache miss rate is just to increase the associativity. So that is the end of the tutorial, and thank you for your time.